everyone. So in today's video, we're going to continue to talk about inverse trig functions. So we're going to do some practice with inverse sine and inverse cosine like we talked about yesterday. And then we'll also introduce inverse tangent. So I want to start by reminding you what the definitions are for inverse sine and inverse cosine. And then we will, like I said, get into inverse tangent. So inverse cosine, which as we said last time, we write as cosine with this little -1 of x. It basically asks you to find an angle. So like I tried to emphasize in yesterday's video, regular cosine or sine or tangent, you plug in an angle and your answer is a number. Inverse cosine is the other way. You plug in a number and out comes an angle. So inverse cosine of x, I'm going to write this a slightly different way than I did last time. I'm going to say inverse cosine of x is equal to theta. So last time I just said is asking you to find an angle theta. It's the same thing. I'm just kind of writing it in a shorter way here. So inverse cosine of x is equal to theta if two things happen. So the first thing is that cosine of that angle has to be equal to whatever originally appeared in those parentheses. And then the other thing that's important is that the angle has to be in the part of the unit circle from 0 to pi. And so why is that part there? Well, basically we talked about this a lot in yesterday's video, but the idea is that if you didn't have that restriction, then there would be lots of different answers, right? Because there are many different angles that have the same cosine value. And so we want to kind of set this up so that if someone says, what's inverse cosine of 1/2 or something like that, we want there to be only one answer. And that's why we have this restriction that the angle has to be in a certain part of the unit circle. And so basically I'll highlight this here so that we can kind of have a visual for this. But this is the part of the unit circle that you want to be looking at for inverse cosine. So you're looking for angles that lie in that part of the unit circle, and specifically that are like between 0 and pi. So they can't be coterminal angles that are bigger than pi. They have to be specifically between 0 and pi in order to be the correct answer. And then inverse sine of x is equal to an angle theta. So same thing, you're plugging in a number and out comes an angle if sine of that angle is equal to the number that was inside the parentheses. And then in this case, we need theta not to be in the interval from 0 to pi, but in the interval from -pi/2 to pi/2. And we looked at an example in yesterday's video where we saw like why 0 to pi wouldn't work. And then we'll actually see today by looking at the graphs of sine and cosine kind of another rationale for why that wouldn't make sense. So let me kind of do something similar here. So if you are doing inverse sine, you want to be looking at this part of the graph. And I'm going to kind of add arrows here because you want to be thinking about 0 to pi/2 and then 0 to -pi/2. So you don't want to be giving answers like, I don't know, what would be a good example, 7 pi/4 or 11 pi/6. You don't want to be giving answers that are in like this part of the unit circle, but that are measured all the way around. Your answers specifically need to be either between 0 and pi or between 0 and, either between 0 and pi/2 or in between 0 and -pi/2. So this is the part of the unit circle that we're going to look at for inverse sine. And then I'll come back to this page when we talk about inverse tangent and we can see how that kind of fits into this picture as well. So let's do a couple of examples. So first example, let's do inverse cosine of 1/2. So this is asking us to look for an angle, and because it's inverse cosine, we're looking between 0 and pi, and we're looking for an angle so that when you take cosine of that angle, you get 1/2. So basically that means our x coordinate on the unit circle is going to be 1/2, right? So that is going to be at an angle of pi/3. So how do I know that? Well, basically, if you know your kind of standard unit circle angles, you know that when you get something like √2/2, then that's going to be a multiple of 45 degrees, or negative √2/2, something like that. When you have 1/2 or square root of 3/2, those are always going to be either multiples of pi/6 or pi/3. And then it's just a matter of kind of figuring out like which angle is this. So in order to get an x coordinate of 1/2, it has to be that the x coordinate is the smaller coordinate compared to the y coordinate. And so that's going to be an angle of pi/3. Inverse cosine of 1/2 is equal to pi/3. And that is because cosine of pi/3 is equal to 1/2. And additionally, because pi/3 is in the interval from 0 to pi. So I know I did a lot of this last time, but just like one more time, and I'll probably mention it again. So just to give an example that would not be correct. So if you were to go to, let's say, negative pi/3. So negative pi/3 would have coordinates of 1/2 and then negative √3/2. So cosine of negative pi/3 is equal to 1/2. However, negative pi/3 does not satisfy the second condition. It's not in the right part of the unit circle. And so again, that's why we add that restriction, is so that you don't have to have these like multiple answers and be uncertain about which one is the right one. It's really just one answer that's going to work. Okay, so let's do a couple more, and we'll do, so the next one's going to be kind of similar to ones we've been doing, but then we're also going to do some that are a little bit different. They're going to bring up something a little bit different. So the next question is to find inverse sine of -1. So now we're looking for an angle where it's, first of all, it has to be between pi/2 and negative pi/2. And then it needs to have sine of that angle be -1. And so that means that the y coordinate should be -1, right? Because that's how you find sine. So the only point on the unit circle with a y coordinate of -1 is this point here. And so in order to make that fit with the kind of format that we're supposed to use for inverse sine, we need to call that angle negative pi/2. So inverse sine of -1 is equal to negative pi/2 because sine of negative pi/2 is equal to -1. And then additionally, negative pi/2 is in the correct interval. So just to, again, give an example that wouldn't work. So if you were to instead think of this angle, so we just measured it this way, right? And we said this is negative pi/2, and that's the right way to think about this angle when you're doing inverse sine. If you instead measured this way and you said, oh, well, it's also 3 pi/2. Well, it's true. It is true that sine of 3 pi/2 is equal to -1. That is totally true. However, it is not true that inverse sine of -1 is 3 pi/2, because 3 pi/2 is not between negative pi/2 and positive pi/2. So I think like one thing that stands out to me about trigonometry is like there's a lot of rules, right? Like a lot of this isn't so much understanding or not understanding, it's just being able to kind of buy into the rules. And the rules in this case are saying, you have to look in this part of the unit circle to get your answer. Okay, so I want to now look at a couple of examples that are a little bit different, but also kind of the same at the same time. So let's say that we wanted to now find inverse cosine of -1/4. So what's different about this one? Well, it doesn't fit in with the points that we're familiar with on the unit circle, right? It's not square root of 2/2, it's not square root of 3/2, it's not 1/2, it's not 1, it's not -1, it's not 0. It's not one of those like familiar angles or familiar points. That does not mean that this point is not on the unit circle. It is, right? So if we're looking in, so we want to be looking in this part of the unit circle, right? And we want to go to, if we want cosine to be -1/4, that means that we want an x coordinate of -1/4. So I'm just going to kind of estimate here. So if this is -1, this would be -1/2. So -1/4 should be somewhere like here. So a point that's like right there on the unit circle is going to have an x coordinate of -1/4. And so basically like that is the angle we're looking for. And we don't really care what the y coordinate is. If you wanted to find the y coordinate, I'm just going to write y because it's not really relevant for this part of the question. If you wanted to find the y coordinate, you could totally find it just using the Pythagorean theorem or using the unit circle equation, right? Because if the point with an x coordinate of -1/4 and an unknown y coordinate lies on the unit circle, it has to satisfy -1/4 squared plus y squared is equal to 1. So you could find the y coordinate if you wanted to. So you don't really have to draw this picture, but I just wanted to draw it just to kind of give you a visual of what you're looking for here. So this, it turns out, this is not going to be a friendly angle. So this is not going to be an angle that is a multiple of pi/3 or pi/6 or pi/4. And so in this case, we actually have to use our calculator. So it's kind of like going back to when we were doing trigonometry with right triangles. You know, there are certain types of angles. So something like cosine of, 45, like that, 45 degrees, you could find that without using a calculator. But there are other angles like cosine of 43 degrees where you do have to use a calculator. And it's the same idea here. So what we're going to do is we're going to basically just type this into a calculator. So you literally just type in inverse cosine, and depending on what your calculator is like, you have to kind of poke around to figure out where inverse cosine is. It might be called arc cosine. So I mentioned that in the last video, that arc cosine is just another way of saying inverse cosine. So depending on your calculator, the button might instead say arc cosine. And so if we type this into a calculator, either way you get the same answer, and it's approximately equal to 1.82 radians. So make sure your calculator is in radians mode. It should be clear like which units you're expected to use. Just make sure it's in that correct unit. So this answer, I think, actually is pretty reasonable because pi/2, so if we look at our angle we found, it's a little bit past pi/2, right? Oops. Pi/2 would be this angle I just drew in green. And so if you type pi/2 into a calculator, it's approximately equal to 1.57. So pi/2 radians, is a little bit less than 1.82 radians. So even though we're very accustomed to doing everything in terms of pi in this section, I don't want you to think that like it's some different world where everything is pi. Like there are other numbers that lie in between everything. It's just that the kind of convenient, nice angles that we like to use, those ones you can kind of do everything and just get nice numbers and all your angles will be in terms of pi. But it's totally fine to go to an angle of like 7.9 radians. That is an angle, and it lies somewhere between the angles that we do have and that we are familiar with. Okay, so we're going to do two more. So let's do another one similar to the last one. So what about inverse cosine of -5/4? So this one, you might realize if you watched yesterday's video, this one is actually going to be undefined because you cannot take inverse cosine of a number that is less than -1 or bigger than 1. So why is that? It's because if you think about what inverse cosine means, it's asking you to find an angle such that cosine of that angle is equal to -5/4. But we know that cosine will never be equal to any number that is less than -1 or more than +1. And -5/4 is -1 1/4, so that's less than -1. So the answer is that it does not exist. So inverse cosine of -5/4 does not exist or is undefined. I don't know how I wrote it last time. I'll just say does not exist. Because there is no angle theta such that cosine of theta is equal to negative 5/4. And if you were to type that into your calculator, it should tell you does not exist or domain error or some kind of error. But I would really hope that you can understand why it doesn't exist without having to type it into a calculator. All right, one more that we do need a calculator for. So let's try to find inverse sine of 0.9. So again, this is not going to be one of the points that we're familiar with on the unit circle, but we can still kind of like figure out approximately where it's going to be, right? So 0.9 is really close to 1. And so because sine is the y-coordinate on the unit circle, we're looking for a point where the y-coordinate is like basically the same or it's like almost 1. And maybe even a little further down, because this part of the unit circle is very flat, so you have to kind of go a little further than you would expect to get that y-coordinate to go down enough. So this would be the angle theta for the problem we're on now. And again, here we don't care about the x-coordinate, but we know the y-coordinate is 0.9. And so we should expect our answer to be a little bit less than pi over 2 this time, right? Just by looking at the picture. And because we know, by the way, like how do we know to draw it here and not somewhere else? It's because we want to make sure it's in the right part of the unit circle. And so because we're doing inverse sine, it has to be between negative pi over 2 and positive pi over 2. So if we type this into a calculator, so you could either type in, depending on your calculator, inverse sine like this, or arc sine. By the way, don't try to type in like sine and then to the -1 power, because it might interpret that wrong. So there should be a special button that's specifically for inverse sine. And so if you type this in, you should get about 1.12 radians. And that kind of fits with what we said before, because remember that pi over 2 was 1.57, and so we're just a little bit off of that at 1.12 radians. Okay, so I want to talk about another way about thinking about these domain restrictions, and we're going to do that by looking at what the graphs of these functions look like. So the other way that we can think about this is if you go back to 141, remember that we talked about how a function can only have an inverse if it's 1-to-1. So remember that a function can only have an inverse function if it is 1-to-1. And what does 1-to-1 mean? It basically means that every input you plug in gets a different output. And so the visual way about thinking about a function being 1-to-1 is this idea of the horizontal line test. So if you have a function that maybe looks like this function is not 1-to-1. So why is it not 1-to-1? Well, if you were to draw a horizontal line across the graph, it would hit the graph more than once. And so what does that mean? Like, why is it a horizontal line? What does that have to do with anything? Well, that means that whatever are the x values here and here, if you were to plug those two different x values into your function, you would get the same y value, right? Because the places where this horizontal line crosses the graph happens at two different x values, but those two x values are at the same height. And so that would tell you that's not 1-to-1, that there's two different inputs that give you the same output. So what does a function look like when it is 1-to-1? Well, it might look something like, let me try to make something that's kind of similar to the last one. Actually, never mind. I'm not going to do that. I'm just going to draw something like this. So this is a function that is 1-to-1. right? Because anywhere that you draw a horizontal line, it's only going to cross the graph one time. So if it hits it once, that's okay. That means that there's only one x value corresponding to that height. So this is a function that is one-to-one. So basically the idea is that if you have a function that is not one-to-one, if you try to come up with the inverse, it's not going to work because you're going to plug in one number and get one input and get two different outputs, right? Because inputs and outputs switch place. So if a function's not one-to-one, it has two different inputs with the same output. And that would mean that its inverse function would have one input with two different outputs, and that's not allowed for functions. Functions, you should just plug in one number and get one clear answer. There should never be ambiguity about what your answer is when you're plugging something into a function. So how do we kind of deal with this issue? Well, you can make a function one-to-one by incorporating a domain restriction. So we can by restricting its domain. So basically kind of like cutting off a piece of the graph in order to make the graph pass the horizontal line test. So I want to look at some pictures now. So we're going to actually start by looking at a function which is, kind of unrelated to what we're doing right now, which is y is equal to x squared. So y is equal to x squared is a function that is not one-to-one, right? It does not pass the horizontal line test. So how do we make this one-to-one? Well, we add this domain restriction where we say x has to be greater than or equal to 0. So we get rid of the left side of the parabola. And so now it is one-to-one, right? Like if any place you draw a horizontal line is only going to cross the graph once. And so if you look at the inverse, so what's the inverse of x squared? It's the square root of x, right? And the inverse function corresponds to that, right? If you look at the original function, it doesn't really match up with the inverse function. So the inverse function is not really the inverse of x squared, it's the inverse of x squared with this domain restriction. So similarly, let's look at the graph of cosine. So here is the graph of cosine of x, y is equal to cosine of x. So this graph is really, really not one-to-one, right? If you draw a horizontal line, like pretty much anywhere, actually I think anywhere, it's going to hit the graph many, many, many times, right? Like if you pick whatever height, even if you say 1, let's say we draw a horizontal line at a height of 1, it's going to keep hitting this graph over and over forever. So this is not one-to-one. So remember that for inverse cosine, we're restricted to looking at the part of the unit circle where x is between, or where the angle is between 0 and pi. And so why is that? It's because that is a restriction that we can apply to our original function that will make it one-to-one. So if I add the restriction that x has to be between 0 and pi, so here's our original function, here's like kind of just the little snippet, it is one-to-one. And basically, if you look back at this graph, like the section that I've highlighted here is really like the very longest section that you could get of this graph without it doubling back. Like as soon as you add a little bit more, it's going to stop being one-to-one. So really like this is the best we can do, even though it looks like you look at this and you're like, is that even a cosine graph? I don't even know what that is. But it is. It captures all of the different heights that the cosine graph can go through before it kind of doubles back on itself. And so what does the graph of inverse cosine of x look like? Well, it's the inverse of just that little snippet of the graph. So I want to come back and look at sine in a second, but I want to just kind of write down something that maybe will help understand like how these ideas are related. So if you have the original function f of x is equal to cosine of x. So the domain of cosine of x is all real numbers, right? If you don't do any restrictions on it, you're allowed to plug in any angle you want. And the range of cosine is -1 to 1, right? Those are the numbers that can come out when you take cosine of any angle. And so now let's think about the inverse. So if you have the inverse function, so inverse cosine of x, the domain and range switch, right? So the domain of inverse cosine, we've already seen this like just a moment ago, that the domain is -1 to 1, right? You cannot plug in a number to inverse cosine that is bigger than 1 or smaller than -1. So the problem though is that as it stands, as we've written it, cosine is not 1 to 1. And so what we need to do is we need to make a change. We basically need to say this is not 1 to 1. So we're going to add a restriction. So what's that restriction going to be? It's that the new domain is just going to be from 0 to pi. So if the new domain is just from 0 to pi, that means that the range of inverse cosine is going to be from 0 to pi. And that's why when you take inverse cosine of an angle, the only angles that come out of it are angles from 0 to pi, right? If you take inverse cosine of any number, the only kind of answer you're allowed to get is between 0 and pi. And that's because that is the range of inverse cosine. And where does that range come from? It comes from the fact that we're restricting the domain of cosine. So I personally think that this is kind of a trickier way to understand it. Like I think looking at the unit circle and just kind of remembering that that is the restriction is maybe a little easier, but I just wanted to kind of at least let you see how it compares in a graph. So I just want to show you also sine because I think it can help explain why we choose the restriction we do for sine. So here's the graph of sine of x. So let's say that we tried to do the same restriction that we did on cosine. So that would be from 0 to pi. Well, that wouldn't work, right? It's not 1 to 1. So that would not be a good restriction to do if we're trying to make our function have an inverse. And so what we want to do instead is go from -pi/2 to pi/2. So here's full graph of sine, here's with the restriction. And so just like inverse cosine, or just like cosine with the restriction, you know, we've gotten a piece of the graph that goes through all the different possible heights. It goes all the way from -1 to +1 without ever kind of doubling back and becoming not 1 to 1 anymore. And so if you look at the graph of inverse sine, it's just the inverse of that kind of truncated portion. So if you have sine of x, so the domain normally would be all real numbers. I'll cross that out in a moment. And the range would be -1 to 1. But we need to add a restriction in order to have this have an inverse. So the restriction is that instead of being from -infinity to +infinity, it's going to be from -pi/2 to +pi/2. And so what that allows to happen is that now when we have the inverse function, so inverse sine of x, so now the domain is -1 to 1. So those are the numbers that we're allowed to plug in. And then what are the numbers that are allowed to come out? What are the types of angles that are allowed to be the answer for for inverse sine? They're angles between -pi/2 and +pi/2. Okay, so last thing in this video I want to do is introduce inverse tangent. And so it's very, very similar to these. You know, if you understand this stuff, it's basically the same. There's a couple things I think make it a little bit trickier, but it's mostly the same. Okay, so actually, let me pull up the graph for a second of tangent because I think it will help us understand the restriction. So for inverse sine, we need to restrict the domain of sine to being -pi/2 to +pi/2. Whereas for cosine, we had to restrict it to be 0 to pi. So let's try to think about what would make sense for tangent. So here's the graph of tangent. So remember, it repeats itself over and over. And each of those kind of little pieces of the graph goes from -pi/2 to +pi/2, then pi/2 to 3pi/2, etc. So what restriction would make sense here? Well, we could just kind of take one of those things, right? Instead of having all of them, let's just take one of them. Then you have a graph that is 1 to 1. So the inverse tangent function is just going to be the inverse of that little portion of the graph. So basically, long story short, when you're doing inverse tangent, you're going to look at the same part of the unit circle as you do for inverse sine. The only difference is that because tangent is undefined at pi over 2 and negative pi over 2, you're not going to get those angles specifically as answers. But for the sake of saying what part of the unit circle we're going to look at, I'm just going to highlight like the same area. And I think it basically won't really come up to the difference between including or not including pi over 2. So we're going to look at this part of the unit circle for inverse tangent. So inverse tangent of x is equal to theta if tangent of theta is equal to x and your angle is in the interval from, and now I'll just use open parentheses because theta can't actually be pi over 2 or negative pi over 2 because then tangent would be undefined. Okay, so let's just do a few examples of inverse tangent. So let's say we wanted to find inverse tangent of -1. So that means that we're trying to look on the unit circle and we're specifically looking for inverse tangent. Remember, we're looking at this part of the unit circle. So we're trying to figure out what could be a possible angle so that tangent of that angle is -1. So this is where I think it's helpful to remember that idea of tangent being the slope. So where would we get a slope of -1? Well, that would happen if you go to negative pi over 4, right? Because at negative pi over 4, the coordinates are root 2 over 2 and negative root 2 over 2. And so if you take those two coordinates and divide them, you'll get -1. So anytime you're looking for inverse tangent of -1 or +1, it's always going to be some kind of multiple of pi over 4, right? Because those are the angles where you're going to, I mean, it's basically only two things. It's either if it's +1, that would be pi over 4, right? Because that's where you get a slope of +1. If it's -1, it's going to be negative pi over 4 because that's where you get a slope of -1 because here your x and y coordinates are the same except for that one is positive and one is negative. So just to give kind of another example, this would be another point on the unit circle. So this would be the point where you have negative root 2 over 2, positive root 2 over 2. That is another angle, so that would be 3 pi over 4. That is another angle, so that tangent of that angle is -1. However, that angle is not in the right part of the unit circle, so it's not the answer. So our answer is just going to be negative pi over 4. So inverse tangent of -1 is equal to negative pi over 4. And that's because tangent of negative pi over 4 is equal to -1. And additionally, negative pi over 4 is in the right part of the unit circle. And I guess I should use parentheses. It's in the interval from negative pi over 2 to pi over 2. Okay, so let's try a couple more. So I think when you have 1 or -1, those are kind of the easiest ones. But these next two I think are a little bit trickier. So what about inverse tangent of negative root 3, let's say. So how would I think about this one? Well, basically, if you have a square root of 3 involved in some way, that means that your angle has to be a multiple of pi over 3 or pi over 6, because those are the only ones that have square root of 3 in their coordinates, right? Like, there's no way that a square root of 3 is just going to magically appear when there wasn't one already. So we know that it has to be a multiple of pi over 6 or pi over 3. Additionally, we know that it has to be in this part of the unit circle, right? Because it's supposed to be negative, and the only way you can get tangent to be negative is if that slope of that line that you're drawing is negative, and that's only going to happen in quadrant 4. So we basically have two options, negative pi over 6 or negative pi over 3. So let's try both of them. So let's try negative pi over 6 and negative pi over 3, and we can just kind of figure out which one is the right one. So it's not going to be like that much work. So what is tangent of negative pi over 6? Well, negative pi over 6 would be like here. And so that's going to have coordinates of root 3 over 2, negative 1/2. So if we wanted to take tangent of that angle, we would do the y coordinate, so that's negative 1/2, over the x coordinate, which is root 3 over 2. So kind of shortcut here is that the when you're dividing and these two denominators are both the same, they're going to cancel each other out. So we can kind of jump a step ahead and just say, okay, that's negative 1 over root 3. And if we rationalize the denominator here, we end up with negative root 3 over 3. And that's not what we're looking for, right? We were looking for just negative root 3 on its own. So that was not the right answer. So that did not work. So let's try negative pi over 3 and really hope that that one will work for us. So tangent of negative pi over 3, so that angle would be down here. And that would have an x coordinate of 1/2 and a y coordinate of negative root 3 over 2. So if we wanted to take tangent of that, that would be the y coordinate, which is negative root 3 over 2, over the x coordinate, which is 1/2. And that would simplify to negative root 3 over 1, which is the same thing as negative root 3. And so that's good, that's our answer. So that tells us that inverse tangent of negative root 3 is equal to negative pi over 3. Because we just showed right above that if you take tangent of negative pi over 3, you get negative square root of 3. And then also negative pi over 3 is in the correct part of the unit circle. So maybe I'll stop it there and I'll let you try. I'm going to give you a few more of these to try with inverse tangent on your own. All right, thank you, and I will see you next time.